In this video, we're going to look at torque and equilibrium to ultimately answer the question of why do things rotate. So jumping into that, torque is a measurement of you can think of it as rotational force, which we define as the force times the distance, or I should say the perpendicular force times the distance from the pivot. And so you're used to this in everyday experience. If you want to open a door, where do you push it? You push it far away from the hinges, right? So you got a door, and you've got the hinges here. You don't push on the door over here, because it's going to be really hard to open it. You push far away. In other words, you can create larger torque with less force by pushing farther away. I think this is something that you've probably seen before in physics. It's probably pretty familiar. So I am going to skim through it pretty quick. But if you have questions or you get stuck, let me know. So the quantity, it is a vector quantity. The variable is the Greek letter tau. It's like a fancy cursive-y kind of T. But again, this is the Greek letter tau. You can look it up. The units are Newton meters, which makes sense for a force times a distance. And the equation is torque equals the force cross product with the distance away from the pivot, or as we typically present it in class, the perpendicular force. Let me rewrite that differently. The force that's perpendicular times the distance. You'll much more often see this, but technically it is a cross product. But if you just think, okay, how much of this force is perpendicular to the distance away, that's what we want to work with. So let's look at an example to help clear this up. A rope is used to lift a drawbridge currently at an angle of 30 degrees relative to the drawbridge. If the drawbridge is 5 meters long and the rope has a tension of 200 newtons, how much torque is it applying to the drawbridge? So with a drawbridge, we're going to have some sort of pivot here. And then we've got our 5 meter long drawbridge. And then we've got some rope. You pull a drawbridge up from the end. We've got some rope that has an angle is equal to 30 degrees. And then we've got some Ft equal to 200. So now we only want the portion of this that's perpendicular. So we need to draw out our diagram here again, Ft. And I've got some perpendicular force and some parallel force. So this is F parallel, this is F perpendicular. And this, we know the angle up here is going to be the same because they're opposite interior angles. This angle is the same as this one. So theta. So this is Ft, and that's going to be sine theta. Because in other words, sine theta is this divided by Ft. F parallel is Ft cosine theta. So torque is just equal to the force perpendicular times the distance, which in this case is Ft sine theta times 5 meters. And so if we run those numbers, we get 200 times sine of 30 degrees times 5 meters, which is 1,000. So 200 newtons, 1,000 times sine of 30 degrees, Newton meters, and then because I don't remember offhand that, we have a 30, 60, 90, then the opposite of 30 is 1, opposite of 60 is square root 3, and opposite hypotenuse is 2. Yeah, so sine of 30 is 1/2. So this is 500 Newton meters is the torque. And technically, if we want to think about it, the torque, it's going to be kind of pointed out of the screen. So I guess for you, out of the screen, because we're going to torque the force, like it's going to cause this kind of rotation. Actually, for you, it'll be that kind. Sorry, it's mirrored on my monitor here. So it's going to, cause it to rotate this way. So it's going to be pointed out of the screen for you. So now that we've talked about torque, we can talk about equilibrium. So an object is in equilibrium if the net force and net torque are equal to 0. And so in other words, it's not moving or spinning. So net force being equal to 0 means that nothing's going to cause it to shift side to side. And net torque of 0 means it's not going to spin this way or that way, even if it was going to stay kind of stationary. So we've got an example here. A classic example is teeter-totter. So 2 children are shown balanced on a seesaw of negligible mass. And so this is just to make it simple. The first child has a mass of 26 kilograms and sits 16 meters from the pivot. If the second child has a mass of 32 kilograms, how far is she from the pivot? So what we need is the net torque. So sigma tau is equal to 0. So in other words, torque of child 1 plus torque of child 2 has to equal 0. And so torque of child 1, if we look at that, the force is negative, and I'm going to label this as 0, and this as, R1 is equal to 16. So torque of child 1 will be the force parallel for child 1 times the distance for child 1, and torque for child 2 will be the force perpendicular for child 2 times distance for child 2, and that's going to equal 0. Well, we know that the force is equal to the weight, so weight of child 1 times the distance. Well, the distance is to the left, so we need to give that a negative value, times negative 1.6 meters. Actually, let me solve this algebraically first before we get into plugging things in. So we want to find distance of child 2. So that means we're going to have distance of child 2 is equal to the force perpendicular for child 1 times the distance for child 1 divided by the force perpendicular for child 2. Force in this case is the weight, so it's going to be m1g times distance 1 over m2g. The g's can cancel, so we get m1 over m2 times d1. So d2 is going to equal, and there should be a negative here, because I had to subtract the f1 parallel over. Now, we notice that the child 1 is in this leftward direction, so I'm going to call that negative. And so we'll get 26 kilograms divided by 32 kilograms times negative 1.6 meters. And that will give us a final value of 1.3 meters. So this is to make the torque 0, because this child will torque it to cause it to spin this direction, the other child will cause it to torque to spin the other direction, and we need to have them balanced to get it to not spin. That's a condition of equilibrium. The second condition, we need to balance all the forces, the net force up and down, so that the teeter-totter isn't, falling into the ground or going upwards. So in that case, we know that the net force has to equal 0. So Fp minus W1 minus W2 equals 0. In other words, Fp equals W1 plus W2. In other words, Fp equals M1G plus M2G. In other words, Fp, if you plug in all those values, you're going to get 568 newtons. So that's the rough idea here behind torque and equilibrium. The last thing I want to touch on is stability, and that is an object is considered stable if its center of mass is located above its base. So a pyramid, the center of mass is right here. And so if we look, it's located above the base, so it'll stand upwards. Something like, shaped like, say this. The center of mass is going to be, somewhere over here maybe. And the base is only this space right here. So in other words, it's going to be pulling, the gravity's going to be pulling on the center of mass. The normal force to keep it from going into the table is going to push up here. And you'll notice this will produce a torque that will cause it to spin in circles like this. In other words, it'll tip over, it'll fall over. That's the idea behind stability. It's just kind of putting the physics terms to what we kind of common sense believe.